Hey guys, here's the intro video to the next unit called Chemical Kenetics. And when you think about what kinetics means, it refers to motion. And chemical kinetics is the study of how fast chemical reactions occur. Not all chemical reactions occur at the same rate. There are some that move very quickly, and there are some which are incredibly slow. And this unit explores why these different reactions may have different rates, as well as what are the factors that influence the rate of a chemical reaction. We can vary the rate by tweaking a few different factors, and also how exactly do the molecules come together? How do they come together in a step-by-step process called a reaction mechanism? Because very few reactions happen in one single step. And by studying the chemical kinetics of a reaction, you actually gain insight into just what the actual physical mechanism is. What's the order in which two or more things combine in order to give you the overall product. What are the factors that influence chemical reactions? Well, number one, the concentration of the reactants. How much of the reactants there are actually influences how quickly they react. This is supposed to spell reactants over here. I don't know what's going on. Reactants. No. Reactants. There you go. So the concentration of the reactants can certainly affect the speed with which a reaction can occur. Also, what else might do it? The physical state of the reactants. When you have two solids sitting on top of one another, not so much. It's really hard for those two things to gain the minimum amount of energy needed to actually collide and react. So what physical state they are, as well as the temperature at which the reaction is taking place. The temperature, the concentration, the physical states, all of these things so far that I've mentioned, they actually all have to do with collisions. And that's the important aspect here. That's the unifying theme among all of these things. Things have to touch and collide in order to react. And on top of that, they also have to react with a minimum energy when they collide. So when two things collide and they do not have the minimum energy, bam, they just fall back apart and remain individual molecules. Different types of reactions require different minimal collision frequencies and minimal collision energies. And when you look at these three things right here, concentration, physical state, and temperature, all of those are related to the collisions or the frequency of a reaction. Let's take a simple reaction where we'll just take generic molecule A turning into molecule B. Can't think of a simpler reaction than that. How do you express the rate? Well, you can observe the rate by measuring the change in concentration of molecule A over time. Notice that I have a negative sign here. This negative sign means that A is disappearing. So I can follow the rate of the reaction by the rate at which A disappears. These brackets over here refer to concentration. When you see a molecule in brackets like that, that's concentration in molar units. The other thing I could do is I could watch the appearance of B over time. Notice here that this B change over time lacks the negative sign that A does. And that's because B is forming. It's a positive concentration change over time. The negative sign means that I'm watching A disappear. The fact that there's a positive or just no sign shown over B, that it is appearing. The other thing I want to point out is I can set these things equal to one another because they're inextricably linked. B doesn't appear unless A appears. So I can follow either the disappearance of A or the appearance of B. And this right here is referred to as the rate expression. When I express rate as a function of either A disappearing or B appearing, it is the rate expression. If your reaction had 2A going to 3B, I could also write the rate expression for this. The rate is equal to, now I'm going to use molar units, but in order to get this in only molar per time units, I must realize that because there are coefficients here in front of the 2, or the 2 and the 3 are coefficients in front of the A and the B, I have to incorporate them into my rate expression. Notice that in this case, because the A had a 2 in front of it and because the B had a 3 in front of it, the rate at which A disappears will not exactly equal the rate at which B appears. In this case, above, it did because the coefficients are 1s. But in the case below, we have 2A going to 3B. So minus 1/2 the rate at which A disappears is equal to 1/3 of the rate at which B appears. So when you have coefficients in your balanced chemical equation, when you write the rate law, you must incorporate them by inverting them. Another example might be A, sorry about that with the arrow, going to 2B. This might be an easier way to sort of think about this. The rate is equal to, I could follow the loss of A in concentration units over time. But because B has a 2 in front of it, B is appearing at twice the rate at which A is disappearing. So if I want these two things to be equal, the fact is that, whoa, that's supposed to be a B. The rate at which A disappears is actually equal to the rate at which 1/2 of the B molecules are appearing. Because this was a 2, I write it as a coefficient there as 1/2. Take a moment to press pause and to ponder that. So let's write a generic equation for any reaction where, let's say, A uppercase and B uppercase represent the reactants and D uppercase represents the products. If we write lowercase letters in front of them that refer to the coefficients in the balanced chemical reaction, any rate expression could be written minus 1/2 1 over A times the change in A's concentration over the change in time. That's also equal to 1 over lowercase b times the change of B's concentration, oops, there should be a little delta in there, over the change in time. And that would be equal to 1 over D positive change in D's concentration over time. So let's use a real example and let's see if you can do this. Let's say for the reaction of 2 moles of hydrogen gas reacting with 1 mole of oxygen gas, oops, there I go again. I'm going to fix this. It should be H2, gas, plus 1 mole of oxygen gas. When we spark that, we get 2 moles of water. Go ahead and pause at this point and see if you can write the rate expression. When you're finished and ready to look at what the answer is, press pause again. Alright, here's the answer. Rate is equal to minus 1/2 the change in the hydrogen concentration over time. It's also equal to minus the change in the O2 concentration over time. And it's finally also equal to 1/2 the positive appearance in concentration units of water over time. What this means is we could follow any one of these things to determine the rate of this chemical reaction. We could follow the disappearance of hydrogen gas, the disappearance of the oxygen gas, or the appearance of the water. Any one of these we could use to determine the rate of this chemical reaction. Here's where we're going to end this first video. Please feel free to watch it again, play it back, or ask questions in class if you still don't get this. Bye-bye.